11th Science, Chapter 13, Hydrocarbons, Part 1, Alkane, Alkenes and Alkynes. Hello students, welcome once again to Chemistry by Madhusina. Let us understand about hydrocarbons, their classification and methods of preparation by the upcoming video.
And their classification. Hydrocarbons are organic compounds containing only hydrogen and carbon. They play an important role in our life as they meet more than 90% of the energy requirements of the world. Also, they are the major sources of various other organic compounds, which we use in different walks of life. Coal and petroleum are complex mixtures of hydrocarbons. Coal tar, a product of destructive distillation of coal, when subjected to fractional distillation, produces various aromatic compounds, including benzene. These compounds are used in the preparation of various industrially useful products, such as polymers like polystyrene, dyes, drugs, etc. Petroleum, on the other hand, is a major source of alkanes and cycloalkanes. When it is subjected to fractional distillation, the various fractions obtained are used as fuels for different purposes. For example, natural gas in the form of CNG, that is, compressed natural gas, and LNG, that is liquefied natural gas, are used as automobile fuels. Liquefaction of petroleum gas renders a very useful domestic fuel in the form of LPG. Kerosene oil is also used as a domestic fuel, but it is more polluting as compared to LPG. Petrol and diesel are also used as automobile fuels. Among the automobile fuels used, CNG or LNG are the clean fuels. That is, these are non-polluting fuels. Other higher hydrocarbons are used as lubricants, solvents for paints, and so on. Hence, we can say that the hydrocarbons act as sources of energy. Now, let us look at the classification of hydrocarbons. On the basis of carbon skeleton, that is, the type of carbon-carbon bonds, hydrocarbons can be classified into three main categories: saturated, unsaturated, and aromatic hydrocarbons. Saturated hydrocarbons are the hydrocarbons consisting of carbon-to-carbon single bonds. Saturated, open-chain, or acyclic hydrocarbons, in which carbon atoms are linked by straight or branched chains, are called alkanes. The general formula for alkanes is CnH2n plus 2, where n is equal to the number of carbon atoms present. For example, propane. Saturated hydrocarbons, in which the carbon atoms join together to form a closed chain, are called cycloalkanes. The general formula for cycloalkanes is CnH2n, where n is equal to the number of carbon atoms present. For example, cyclopropane. Unsaturated hydrocarbons consist of one or more carbon-to-carbon multiple bonds. That is, a double bond or a triple bond or both. Unsaturated, open chain or acyclic hydrocarbons, in which carbon atoms are linked by straight or branched chains containing at least one carbon-to-carbon double bond, are called alkenes. The general formula for alkenes is CnH2n, where N is equal to the number of carbon atoms present. For example, propene. Unsaturated, open chain or acyclic hydrocarbons in which carbon atoms are linked by straight or branched chains containing at least one carbon-to-carbon triple bond are called alkynes. The general formula for alkynes is CnH2n-2, where N is the number of carbon atoms. For example, propyne. Aromatic hydrocarbons are cyclic hydrocarbons with alternative double bonds in conjugation. Aromatic compounds are benzene and the compounds that resemble benzene in their chemical behavior. For example, benzene, toluene, etc. Alkanes can be obtained in a laboratory either from unsaturated hydrocarbons, alkyl halides, or carboxylic acids. Let's look at each one in detail. Unsaturated hydrocarbons, like alkenes, react with hydrogen in the presence of finely divided catalysts, like platinum, palladium, or nickel, to form alkanes. As this reaction involves addition of hydrogen, it is called hydrogenation. The surface of these metals absorb hydrogen gas and activate the hydrogen-hydrogen bond. The reaction using platinum and palladium can be catalyzed at room temperature. However, the reaction using nickel as a catalyst requires relatively higher temperature and pressure. For example, ethene on hydrogenation in presence of catalysts such as finely divided platinum, palladium, or nickel gives ethane. To obtain alkanes from alkyl halides, we can either use the reduction method or the Wurtz reaction. Alkyl halides on reduction with reducing agents such as zinc copper couple in ethanol or zinc and dilute HCl gives alkanes. For example, ethyl iodide when reduced by using zinc copper couple in ethanol or zinc and dilute HCl gives ethane. Now let's see how to obtain alkane from alkyl halides using the Wurtz reaction. Alkyl halides, on treatment with metallic sodium in presence of dry ether, give higher alkanes with even number of carbon atoms. This reaction is known as Wurtz reaction. For example, the reaction of bromomethane with sodium metal in presence of dry ether gives ethane. It is important to note that when two different alkyl halides are taken, then a mixture of alkanes is produced. For example, the Wurtz reaction of mixture of methyl iodide and ethyl iodide forms ethane, butane, and propane respectively. As alkanes have close boiling points, it becomes very difficult to separate them from the mixture. Hence, this method is not suitable to prepare the alkanes with odd number of carbon atoms. Now, let's see how alkanes can be prepared from carboxylic acids. Sodium salts of carboxylic acids on heating with soda lime give alkanes with one carbon atom less than the parent carboxylic acid. Soda lime is a mixture of calcium oxide and sodium hydroxide. As this reaction involves the elimination of carbon dioxide from a carboxylic acid molecule, the process is known as decarboxylation. For example, sodium propionate on heating with soda lime gives ethane. Coal-based electrolytic method is yet another method to prepare alkanes from carboxylic acids. This method involves the preparation of alkanes with even number of carbon atoms through the electrolysis of aqueous solutions of sodium or potassium salts of carboxylic acids. For example, the aqueous solution of sodium or potassium acetate on electrolysis gives ethane. The mechanism of the reaction can be understood through the following steps. At anode, the acetate ions in the solution lose electrons at the anode and form acetate free radicals. The acetate free radical lose carbon dioxide molecule and thus form methyl free radicals. The methyl free radicals further react and form ethane gas. At cathode, water molecules accept the electrons and split up into hydroxyl ions and hydrogen free radicals. Two such hydrogen free radicals combine together and form hydrogen gas. Thus, in coal-based electrolysis method, alkane is produced at the anode. First, let's look at the physical properties. These include appearance, color, odor, boiling point, solubility, and polarity, among others. These properties depend on the attractive forces working on the molecules. As we have learned, alkanes consist of only carbon-to-carbon and carbon-to-hydrogen single bonds. These bonds are covalent, and the electronegativity between two carbon atoms or between carbon and hydrogen is almost negligible. Hence, the molecules formed are non-polar. This is why the only attractive force acting on these molecules is the weak van der Waals forces. Therefore, the first four members of the series, C1 to C4, are gases. C5 to C17 are liquids, while the molecules containing 18 or more than 18 carbon atoms are solids at 25 degrees Celsius. They are all colorless and odorless. Due to their non-polar nature, these compounds are insoluble in polar solvents like water and soluble in non-polar solvents like benzene. Their boiling point is decided by the strength of the van der Waals force. This force is very sensitive to distance. Hence, for a strong force of attraction, the molecules need to be held close together. However, in alkanes, because of their non-polar molecules, the van der Waals forces are weak, and hence, their boiling points are much lower than expected. As the size of a molecule increases, its surface area increases. Thus, the strength of the intermolecular van der Waals force also increases. A linear or straight chain alkanes, like pentane, has a higher boiling point than its branched isomers, like 2-methylbutane and 2,2-dimethylpropane. This is because branching reduces the surface area of a molecule, leading to a weakening of the van der Waals forces, which are then overcome at relatively lower temperatures. Now, let's look at the chemical properties of alkanes. As we have seen, alkanes are non-polar. Their carbon bonds are quite stable, and so they do not easily react with acids and bases. However, they do undergo substitution reactions and combustion reactions under certain conditions, as their carbon atoms are in strongly reduced states. During this reaction, the hydrogen atom of an alkane is substituted, and hence, the reactions are called substitution reactions. When the element substituting the hydrogen is a halogen, the reaction is called halogenation. It involves 3 steps: initiation, propagation, and termination. Let's go through each step by observing the chlorination of methane. During chlorination of methane, the 4 hydrogen atoms of methane are step by step substituted or replaced by chlorine atoms, forming tetrachloromethane as the final product. During initiation, the chlorine molecule is homolyzed in the presence of heat or light, forming chlorine-free radicals. During propagation, 2 reactions take place. First, the chlorine-free radical attacks the methane molecule, forming a methyl-free radical and hydrogen chloride. Next, the methyl-free radical attacks the second chlorine molecule, forming chloromethane, and one more chlorine-free radical, setting up the chain reaction. The chlorine-free radical formed sets up many other propagation steps to form more halogenated products. These steps are repeated till all the hydrogen atoms in the methane molecule are replaced by chlorine atoms. During termination, the reaction stops either because all the reactants have been consumed or because of the following possible chain terminating reactions. One possible reaction is that 2 chlorine-free radicals combine to form a chlorine molecule. Another possible reaction is that 2 methyl-free radicals combine to form ethane. Or a chlorine-free radical and a methyl-free radical combine to form chloromethane. Thus, in the chlorination of methane, ethane is obtained as a byproduct. Now let's understand the combustion reaction of alkanes. On heating, alkanes get completely oxidized to carbon dioxide and water along with heat. In the presence of air or dioxygen. This is why alkanes are used as fuels. When alkanes undergo incomplete combustion, they form carbon black. It is used in the manufacturing of ink, printer ink, black pigments, and as filters. Alkanes, like methane, on heating at high pressure with a regulated supply of oxygen and in the presence of a suitable catalyst, provides a variety of products like methanol and methanal. Ethane gives ethanoic acid. And an alkane with tertiary hydrogen atom like 2-methylpropane gives corresponding alcohol. When a normal alkane like N-hexane is heated in the presence of anhydrous aluminium chloride and hydrogen chloride gas, it isomerizes to a branched chain alkane like 2-methylpentane and 3-methylpentane. Alkanes undergo aromatization or reforming. That is, a normal alkane with 6 or more than 6 carbon atoms, like N-hexane, when heated to 773 Kelvin at 10 to 20 atmospheric pressure in the presence of a catalyst like oxides of vanadium, molybdenum, or chromium, supported over alumina, gets dehydrogenated to form cyclic compounds like benzene or its homologs. Alkanes also react with steam. This reaction is used in the industrial preparation of dihydrogen gas. For this, methane is heated at 1000 degrees Celsius in the presence of nickel, along with steam to form carbon monoxide and dihydrogen gas. Higher alkanes at higher temperatures decompose to form lower alkanes and alkenes, amongst others. This reaction is also known as pyrolysis, or alkanes with two or more carbon atoms, like ethane and propane, consist of carbon-to-carbon single covalent sigma bonds, in which the electrons are shared symmetrically around the internuclear axis of the carbon-carbon single bonds. The atoms within a molecule are in constant rotational movements along the internuclear axis, as the molecular orbitals are not disturbed due to rotation. Due to this, the shape of an alkane molecule can be twisted into different three-dimensional arrangements by rotation about the carbon-to-carbon, single bond, or bonds. These different three-dimensional arrangements are interchangeable and are called conformations. These interconversions are very rapid, and hence, in a short span of time, a given molecule may exist in infinite different conformations. However, remember, conformations do not affect the bond angle and the bond length. Now let's understand the concept of conformation better by using the ethane molecule as an example. We can see that each carbon atom is attached to one carbon and three hydrogen atoms. Now, imagine one of the carbon atoms along with its hydrogen bonds rotating around the internuclear axis of the carbon-to-carbon bond. You can see that this rotation causes infinite different spatial arrangements of the hydrogen atoms of one carbon atom with respect to the hydrogen atoms of another carbon atom. These arrangements are called conformational isomers. In reality, both the carbon atoms will be going through such rotations, thus increasing the number of spatial arrangements. Let's study these in detail. We can observe that there are two extreme positions of the hydrogen bonds of one carbon in relation to the hydrogen bonds of another carbon atom. One, where the hydrogen atoms attached to the two carbon atoms are as close as possible to each other, and the other where they are as far apart as possible. When the arrangement has the hydrogen atoms close to each other, the three hydrogen atoms and carbon atoms at the back are hidden by the three hydrogen atoms attached to the carbon atom in the front. And so the arrangement is known as Eclipsed Conformation. The arrangement wherein the hydrogen atoms are far from each other, the three hydrogen atoms and carbon atoms at the back are visible behind the three hydrogen atoms attached to the carbon atom in the front, giving the arrangement a neatly distributed look. And so the arrangement is known as staggered conformation. All the arrangements between the eclipsed and staggered positions are known as skew conformations. In the eclipsed conformation, the molecule is the least stable as the repulsive force between the electrons is the maximum. This is due to close spatial arrangement of the carbon-hydrogen bonds. In the staggered conformation, the molecule is the most stable, as there is minimum repulsive force between the electrons. This is because the carbon-hydrogen electrons are the farthest from each other. The repulsive interaction between the electron clouds in a molecule, which affects the stability of a conformation, is called torsional strain. Its magnitude depends upon the angle of rotation about the carbon-to-carbon bond. This angle is known as torsional or dihedral angle. The energy difference between eclipsed and staggered conformations is 12.5 kilojoules per mole, which is easily overcome at room temperature and pressure. Due to this, it is not possible to separate different conformation isomers of ethane. Now that we have seen what conformation means, let's learn the two standard visual representations used to explain it. These are known as Sawhorse projection and Newman projection. In Sawhorse projection, the molecules are viewed along their molecular axis, that is, at an oblique angle. Here, the carbon-to-carbon bond is shown as a long straight line, whose upper end is bent slightly either towards the left or towards the right-hand side. The front carbon is shown at the lower end of the line and the back carbon at the upper end. Each carbon has 3 hydrogen atoms attached to it. These bonds are shown with the help of 3 lines attached to the carbon atom. These are inclined at an angle of 120 degrees to each other. Using Sawhorse projection, the 3-dimensional structure of the eclipsed and staggered conformations can be easily visualized. In Newman projection, the carbon-to-carbon bond conformation is viewed head-on, that is, front to back. The carbon atom at the front is represented as a dot, and the carbon atom at the back is represented as a circle. The hydrogen atoms attached to the carbon atoms are shown by lines. The bond angle between these lines is kept at 120 degrees. The hydrogen atoms connected to the carbon atom in the front are represented by longer lines, and those connected to the carbon atom at the back are represented by shorter lines. Using Newman projection, an unsaturated hydrocarbon with a double bond in between the carbon atoms is called an alkene. Alkenes are also called olefins, which means oil forming, as its first member Ethyne. Alkenes can be prepared from alkynes, alkyl halides, vicinal dihalides, and alcohols. Let's look at each of them in detail. To obtain alkenes from alkynes, we carry out partial catalytic hydrogenation. During this reaction, addition of a hydrogen molecule, that is, addition of 2 hydrogen atoms, takes place across the triple bond of the alkyne. There are 2 catalysts that are commonly used. One is palletized charcoal, which is partially deactivated using compounds like barium sulfate or quinoline. It is also known as Lindlar's catalyst. The other catalyst is sodium in liquid ammonia. For example, ethyne, on reduction with palletized charcoal or sodium in liquid ammonia, forms ethane. Similarly, propyne, on reduction with palletized charcoal or sodium in liquid ammonia, forms propene. Depending upon the nature of the catalyst used, a higher alkyne can be reduced to cis or trans alkene. Lower alkynes, such as ethyne and propyne, and higher terminal alkynes do not yield cis-trans isomers upon hydrogenation. When the catalyst used is Lindlar's catalyst, the alkene obtained shows cis geometry. When the catalyst used is sodium in liquid ammonia, the alkene obtained shows trans geometry. For example, 2-butyne, on reduction with palletized charcoal in presence of quinoline, forms cis-2-butene. However, 2-butyne, on reduction with sodium in the presence of liquid ammonia, forms trans-2-butene. Alkenes can also be obtained from dehydrohalogenation of alkyl halides. When an alkyl halide is heated in presence of alcoholic potash, it gives an alkene, and one molecule of halogen acid is eliminated in the reaction. The hydrogen atom for the halogen acid is obtained from the carbon atom adjacent to the carbon atom attached to the halogen atom. The carbon atom attached directly to halogen is called alpha carbon, whereas the adjacent carbon is called beta carbon. Hence, the reaction is known as beta elimination reaction. As hydrogen and halogen atoms are removed in the form of halogen acid from alkyl halide, the reaction is also known as dehydrohalogenation reaction. For example, 1-chloroethane, on heating with alcoholic potassium hydroxide, forms ethene. During this reaction, the hydrogen and halogen atoms on adjacent carbon atoms of 1-chloroethane are eliminated in the form of hydrochloric acid. In a dehydrohalogenation reaction, if there are two possible positions where the double bond can be formed, then the product obtained is governed by Saint-Zeff's rule. Saint-Zeff's rule states that elimination will predominantly proceed to the formation of olefin in which the double bond is highly substituted. In other words, the hydrogen atom will be removed from the carbon atom possessing lesser number of hydrogens. The rate of reaction depends on the nature of alkyl group and the halogen respectively. The rate increases from primary to tertiary alkyl halides as shown here. The rate is also affected by the halogen atom attached and is the highest for iodine and lowest for chlorine. Another way to obtain alkenes is by the dehalogenation of vicinal dihalides. In vicinal dihalides, the two halogen atoms are attached to two adjacent carbon atoms. When such dihalides are treated with zinc metal, the zinc atom removes the two halogen atoms, forming zinc halide, leaving behind an alkene in the process. This reaction is also called dehalogenation, as zinc removes two halogen atoms simultaneously. For example, when dibromoethane is treated with zinc, it forms ethene and zinc bromide. And when 1,2-dibromopropane is treated with zinc, it forms propene and zinc bromide. Alkenes can also be obtained from alcohol using acidic dehydration process. When heated with concentrated sulfuric acid, the OH group of the alcohol and one hydrogen atom from the adjacent carbon atom are eliminated in the form of a water molecule, forming an alkene. Hence, the reaction is said to be acidic dehydration of alcohol. An example of this would be the dehydration reaction of ethanol on heating with concentrated sulfuric acid to form ethene. During this reaction, the hydrogen atom and the hydroxyl group from adjacent carbon atom are eliminated in the form of water to form ethene. For example, in the dehydration of 2-butanol, there are two possible positions for the double bond. However, 2-butene is more substituted than 1-butene. Hence, the more predominant product is 2-butene. Thus, we see that alkenes can be obtained by many different methods. Now let us look at the physical properties of alkenes. Alkenes are colorless hydrocarbons. Except for ethene, all the other alkenes are odorless as well. The first three members of alkene homologous series are gases. The 4th to 14th are liquids. And all members above 15th are solids. Being non-polar compounds, alkenes are insoluble in water, but soluble in non-polar solvents like benzene and petroleum ether. Alkenes are unsaturated hydrocarbons consisting of a sigma bond and a pi bond. The typical reactions of alkenes involve the breaking of the weak pi bond to form two sigma bonds. Such reactions are called addition reactions. These addition reactions are usually electrophilic in nature, as the pi electrons of carbon-carbon double bond are available to any species seeking electrons. Let us study the following reactions in alkenes. Addition of dihydrogen, addition of halogens, addition of halogen acid, addition of sulfuric acid, addition of water, oxidation, ozonolysis, polymerization. Let's start with addition of dihydrogen to alkene. Alkenes react with dihydrogen in the presence of catalysts like finely divided nickel, palladium, or platinum to form alkanes. Such addition reactions are always cis addition reactions. For example, ethene in the presence of finely divided nickel, palladium, or platinum yields ethane. Similarly, propene yields propane. Now let's look at the addition of halogen to an alkene. Alkenes react with halogens such as chlorine and bromine to form vicinal dihaloalkanes. However, they don't react with iodine under normal conditions. For the reactions with chlorine and bromine, the alkenes and the halogens are mixed together in an inert solvent like carbon tetrachloride. Ethene reacts with bromine to give 1,2-dibromoethane. This reaction proceeds via the formation of an intermediate called cyclic bromonium ion. During the addition reaction between ethene and bromine, the reddish-brown color of bromine gets decolorized due to the formation of dibromoethane. Hence, this reaction is used as a test for unsaturation. Let us now look at the addition of halogen acid. Alkenes react with halogen acids to form haloalkanes. In the reaction with alkenes, hydrogen iodide is more reactive than hydrogen bromide, which is more reactive than hydrogen chloride. In the case of symmetrical alkenes, only one product is formed. For example, ethene on reaction with hydrogen bromide gives bromoethane, or 2-butene with hydrogen bromide gives 2-bromobutane. However, in the case of unsymmetrical alkene, two products are formed. For example, propene reacts with hydrogen bromide to form 2-bromopropane and 1-bromopropane. Of these, 2-bromopropane is a major product. This is in accordance with Markovnikov's rule, which states that during the addition of an unsymmetrical reagent to an unsymmetrical alkene, the negative part of the addendum is added to that unsaturated carbon which possesses lesser number of hydrogen atoms. In the reaction between propene and hydrogen bromide provides the electrophile H+ that attacks the carbon-carbon double bond, leading to the formation of primary and secondary carbocations. The secondary carbocation, being more stable, is formed readily. This secondary carbocation is attacked by the bromide ion to form 2-bromopropane. Hence, 2-bromopropane is a major product. However, the addition of hydrogen bromide to unsymmetrical alkenes, like propene, in the presence of peroxide, is on the contrary to Markovnikov's rule and is known as anti-Markovnikov's addition or peroxide effect or Kharash effect, as it was first observed by M.S. Kharash and F.R. Mayo in 1933 at the University of Chicago. The peroxide effect takes place via the free radical mechanism. In this reaction, initially benzoyl peroxide undergoes homolysis to form benzene free radical. This attacks hydrogen bromide and results in the generation of a bromine free radical. This bromine free radical further propagates the reaction by attacking the double bond in propene. Hence, propene undergoes homolytic cleavage to produce less stable primary and non-stable secondary free radicals, as shown here. The secondary free radical attacks hydrogen bromide to form bromopropane, and the primary free radical attacks hydrogen bromide to form 2-bromopropane. Thus, 2-bromopropane is formed as the major product. Now let us move to the addition reactions of alkene with sulfuric acid and water respectively. Alkenes react with cold concentrated sulfuric acid in accordance with Markovnikov's rule to form alkyl hydrogen sulfates. For example, ethene and propene react with cold concentrated sulfuric acid and form ethyl hydrogen sulfate and propyl hydrogen sulfate respectively. Alkenes react with water in accordance with Markovnikov's rule. In the presence of concentrated acids, like sulfuric acid, a water molecule adds to an alkene molecule across the double bond to form alcohol. For example, 2-methylpropene reacts with water in presence of concentrated sulfuric acid to form 2-methylpropan-2-ol. Let us now look at the oxidation reactions of alkenes. Alkenes, on reacting with cold dilute aqueous solution of potassium permanganate, which is also called Bayer's reagent, produce vicinal glycols, that is, 1,2-diols. For example, ethene, on reaction with Bayer's reagent, forms ethane 1,2-diol or ethylene glycol. As the purple color of potassium permanganate decolorizes with the formation of glycol, this reaction is used as a test for unsaturation. Depending on the nature of alkene and experimental conditions, alkenes react with oxidizing agents such as acidic potassium permanganate or acidic potassium dichromate to form ketones or acids. For example, 2-methylpropene, on reacting with acidic potassium permanganate, gives propan-2,1 or acetone. On the other hand, but-2-ene, on reacting with acidic potassium permanganate, gives ethanoic acid. Let us now look at the addition of ozone to an alkene, which is also called ozonolysis. Alkenes react with ozone to form ozonides, which, on further hydrolysis, in the presence of zinc, form either aldehydes or ketones or both. For example, in this reaction, the ozone molecule is added across the double bond in ethene to give ethene ozonide. This, on hydrolysis, forms formaldehyde or methanol. The oxidation of alkenes by ozone to form ozonides, followed by its decomposition with water, is termed as ozonolysis. This reaction is useful in locating the position of the double bond in an unsaturated molecule. Let us look at another example of ozonolysis reaction of propene. Here, first propene and ozone react to form propene ozonide. The propene ozonide, on further hydrolysis, in the presence of zinc, undergoes cleavage to form ethanol and methanol. The products formed helps us to determine the position of the double bond in propene as shown here. Let us move on to the last reaction, that is, polymerization. Alkenes undergo addition polymerization reaction when heated under pressure in the presence of suitable catalysts. In this, a large number of molecules of the same species join together to form a giant molecule called a polymer. The simple compound which forms the polymers are called monomers. For example, ethene, when heated to 1000 degrees Celsius, under 1000 atmospheric pressure, undergoes polymerization to form polyethene. H2n minus 2 is known as alkynes. Alkynes contain at least one triple bond between two carbon atoms. The first of the alkyne series is ethyne, with the chemical formula C2H2. Ethyne, also known as acetylene, is used for arc welding in combination with oxygen gas, which is known as oxyacetylene flame. Alkynes have less number of hydrogen atoms than that of alkanes and alkenes. Hence, though their names are different, the nomenclature of alkynes is invariably dependent on the corresponding alkane. In the IUPAC system, alkynes are named by replacing the ane of the corresponding alkanes by the suffix yne. For example, ethane becomes ethyne, and propane becomes propyne. In a structure, the carbon atom with the triple bond is assigned the lowest number. This lowest possible number of the carbon atom also denotes the position of the triple bond. However, in some alkynes, there may be more than one possible structure because the position of the triple bond may be different in each structure. For example, pentyne has two structures, as shown here. In one structure, the position of the triple bond is 1, whereas in the other, it is 2. They are named as pent-1-ine and pent-2-ine. When two compounds differ in their structures due to the position of their triple bond, they are known as position isomers. Let's see if we can arrange the atoms in a different way to get another different structure. You can see that we got a chain structure of the same compound. Such a structure is known as a chain isomer. In this structure, the position of the triple bond is 1. Therefore, the name of the isomer will be 3-methyl-but-1-ine. Now let's understand the structure of ethyne molecule in relation to a triple bond. An ethyne molecule has two hydrogen atoms bonded to two carbon atoms. Each carbon atom has two sp hybridized orbitals and two unhybridized p orbitals. The head-on overlapping of the two sp hybridized orbitals of the two carbon atoms forms a carbon-carbon sigma bond. The sp hybridized orbital of each carbon atom overlaps with the 1s orbital of each hydrogen atoms along the internuclear axis. This overlapping forms two carbon-hydrogen sigma bonds. The hydrogen-carbon-carbon bond angle is 180 degrees. The unhybridized p orbitals in each carbon atom lie perpendicular to each other as well as to the plane of the CC sigma bond. The two p orbitals undergo lateral or sideways overlapping, forming two pi bonds between the two carbon atoms. Hence, an ethyne molecule consists of one carbon-carbon sigma bond, two carbon-hydrogen sigma bonds, and two carbon-carbon pi bonds. The electron cloud between two carbon atoms is cylindrically symmetrical about the internuclear axis. Therefore, the shape of ethyne molecule is linear. The carbon-carbon triple bond is shorter than carbon-carbon double or single bond. As the triple bond is shorter, it is stronger compared to single and double bonds. First, let's look at the industrial preparation of ethyne from calcium carbide. In this method, initially limestone is subjected to thermal decomposition, in which it results in the formation of quicklime. Quicklime obtained is heated to high temperatures with coke to get calcium carbide. When this calcium carbide is subjected to hydrolysis, ethyne or acetylene is formed. Alkynes can also be prepared from vicinal dihalides, that is, 1,2-dihaloalkanes. A vicinal dihalide molecule has two halogen atoms, each linked to two adjacent carbon atoms. When treated with alcoholic potash, the molecule undergoes dehydrohalogenation. In dehydrohalogenation, first, an atom of halogen on one carbon and an atom of hydrogen present on adjacent carbon in the alkyl dihalide are eliminated as one molecule of hydrogen halide. This results in the formation of alkyl halide. This alkyl halide, when treated with a strong base such as sodamide, another molecule of hydrogen halide is eliminated, thus resulting in the formation of an alkyne. For example, when 1,2-dichloroethane is treated with alcoholic potassium hydroxide, forms vinyl chloride, and this, when treated with sodamide, forms ethyne. Do you know why a strong base like sodamide is required for the formation of ethyne from vinyl chloride? As the chlorine atom is directly attached to double-bonded alkynes, follow the same physical characteristics of their predecessors, alkanes and alkenes. The first three alkynes of the series are gases. The alkynes from the 4th to the 11th in the series are liquids, while the higher ones in the series are solids. All alkynes are colorless and odorless, except ethyne, which has a characteristic smell. The CH bond attached to carbon atom with triple bond in alkynes. Alkynes exhibit some polarity, unlike alkenes and alkenes, which are non-polar. This is because the CH bond in alkynes is slightly polar due to the sp hybridization of carbon. As alkynes are non-polar and water is polar, alkynes are water insoluble. However, they dissolve in non-polar organic solvents like ethers, carbon tetrachloride, and benzene. The melting point, boiling point, and density of alkynes are directly proportional to their molecular masses. Coming to their chemical properties, alkynes exhibit more acidic behavior than alkenes and alkenes. For example, sodium metal reacts with ethyne, forming monosodium ethanide and disodium ethanide. Similarly, propene with one hydrogen atom attached to triple bond carbon atom on reaction with soda amide forms sodium propionate. Sodium metal and sodamide are strong bases and do not react with alkanes or alkenes, as they are not acidic. This shows that alkynes are more acidic in nature than alkanes and alkenes. Let's understand why. The hydrogen atoms in ethyne are attached to the sp hybridized carbon atoms. On the other hand, the hydrogen atoms in ethene and ethane are attached to the sp2 and sp3 hybridized carbon atoms, respectively. The sp hybridized orbitals of carbon atoms in ethyne molecules have 50% of s character and hence the highest electronegativity. These electronegative orbitals attract the shared electron pair of the carbon-hydrogen bond towards the carbon of ethyne to a greater extent than the sp2 and sp3 hybridized orbitals of carbon in ethene and ethane. Therefore, the hydrogen atoms in ethyne can be liberated easily as protons. This makes the hydrogen atoms of ethyne, which are attached to the triply bonded carbon atom, acidic in nature. The addition reactions in alkynes are electrophilic in nature due to the availability of loosely held pi electrons. As alkynes contain a triple bond, during an addition reaction, they add two molecules of dihydrogen, halogen, or hydrogen halides to form a saturated molecule. Vinylic cation is formed as an intermediate during the addition reaction of an alkyne. Whereas alkyl carbocation is formed as an intermediate during the addition reaction of an alkene. As vinylic cation is less stable than alkyl carbocation, alkynes are less reactive towards the addition reactions than alkenes. Hence, the addition reactions of alkynes takes place under drastic conditions when compared to the addition reactions of alkenes. Let's go through some addition reactions of alkynes. An alkyne reacts with two molecules of dihydrogen in the presence of suitable catalysts like finely divided nickel, platinum, or palladium to form the corresponding alkane. For example, propyne reacts with two molecules of dihydrogen in the presence of finely divided nickel as catalyst to form propane. Alkynes form dihaloalkene when treated with one molecule of halogen and form tetrahaloalkane when treated with two molecules of halogen. For example, when ethyne reacts with one molecule of bromine, it forms 1,2-dibromoethene. And when it reacts with two molecules of bromine, 1,1,2,2-tetrabromoethane is formed. The reddish-brown color of bromine decolorizes due to the formation of saturated 1,1,2,2-tetrabromoethane. Thus, this reaction is used as a test for unsaturation. Alkyne, when treated with two molecules of hydrogen halide, forms gem dihalide. On the other hand, when treated with one molecule of hydrogen halide, it forms alkynyl halide. Addition in unsymmetrical alkynes takes place in accordance with Markovnikov's rule. This rule says that in an electrophilic addition reaction, the negative part of an addendum attaches itself to the unsaturated carbon atom of the molecule having lesser number of hydrogen atoms. For example, propyne reacts with two molecules of hydrogen bromide and forms 2,2-dibromopropane in accordance with Markovnikov's rule, as shown here. Like alkanes and alkenes, alkynes are also immiscible and do not react with water. However, in the presence of dilute sulfuric acid and mercuric sulfate at 60 degrees Celsius, alkynes add one water molecule to give aldehydes or ketones. For example, ethyne reacts with a water molecule in the presence of dilute sulfuric acid and mercuric sulfate at 60 degrees Celsius to give ethanol. Similarly, propyne reacts to give propanone. Polymerization is of two types: linear polymerization and cyclic polymerization. When heated in the presence of a catalyst, alkynes undergo polymerization. In linear polymerization, the alkyne molecules form a long-chain polymer. For example, linear polymerization of ethyne produces polyacetylene or polyethine. Polyethine is a high molecular weight polyene which consists of repeating units as shown here. The polyethine molecule is represented as shown. It conducts electricity under special conditions. This is why a thin film of polyethine is used as an electrode in batteries. In cyclic polymerization, alkyne molecules add to each other, resulting in the formation of a cyclic compound. For example, when ethyne is passed through a red-hot iron tube at 873 Kelvin, it undergoes cyclic polymerization. In this cyclic polymerization, 3 molecules of ethyne polymerize to form benzene. Because of their polymerization abilities, alkynes combine to form many different compounds. For example, benzene obtained by the polymerization of acetylene is used for the preparation of dyes, drugs, and a large number of other organic compounds.